really like unit circle centric lately. Everything's on the unit circle. Find an angle, it matches an angle on the unit circle. Find the trig functions, all those things. But today, the other part of section 4.4 talks about how to do trig functions for any angle. So what I mean by any angle is an angle that's not necessarily on the unit circle. Now, could it be on the unit circle? Sure. But these are more for like general angles that aren't necessarily on the unit circle. Well, obviously, one way we can do trig ratios for angles that aren't on the unit circle, if we're given an angle, we're going to use a calculator, right? And way back when, before our calculators had trig functions, we would have a book of tables, and you would have to look up the trig ratio on a table, and it would have like a decimal value. Okay. But these problems that we're going to do today, I'm actually not going to give you the angle. So you don't know the value of the angle, but you can find the trig ratios. So this first part is really like a definition. If you look this up in a textbook, and you should have done this one in Algebra 2, it's going to be like something that was in a box, right? Like, remember this thing. These things are true. Of course, it starts with let theta be an angle in standard position. Well, all the thetas that we're working with in this chapter are in standard position, unless it's like in some like geometric triangle. But all of our thetas are going to be in standard position, so initial side on the positive x-axis, terminal side opens up around the origin. XY is a point on the terminal side. So here's where the big difference is from the stuff we were doing last week. Okay, here's my positive x-axis initial side, and then here's my terminal side, and I'm opening up. Suppose my terminal side ends here in quadrant 2. Okay. On this arm, there are infinitely many points, x and y, that are on the terminal side of that angle. And what we would have focused on last week was one of those xy points that would have made my radius 1, so that I was actually on the unit circle. And then, of course, my angle had to be one of the special angles, 30, 45, or 60-degree reference angles. Okay, but what we're talking about today is I could be any point anywhere on this arm, on this terminal side. Can you then find me the 6 trig ratios? Okay, is basically the question. So I'm going to start by drawing a picture. I had mentioned this when we did the definition for these trig functions on the unit circle, that we would draw this picture over and over again in this chapter and our next chapters. Okay, so here we go. It's our second go-around drawing essentially the same picture. There's an angle in standard position. I put the terminal side in quadrant 1 so that our picture always looks the same, but the terminal side could really be in any quadrant. And now we're not confined to the one circle that has the radius of 1. We can be any circle out, but we know that there is some point xy on our terminal side. Okay, where that is, we don't necessarily know. But if we're trying to find these trig ratios, we're essentially looking for a triangle. Okay. When you draw your triangles, whether it's in quadrant 1, quadrant 2, quadrant 3, or quadrant 4, it needs to be part of a bow tie, whether it's a special angle or not. So you always take this point back to your horizontal x-axis. Okay, so you're building a triangle that's part of a bow tie. And then think about what you know about this triangle if this point xy is on that terminal side. From the origin, I went right x and up y to get to that point, didn't I? So sides are x and y. If it were a unit circle, I would know that the radius was 1, but I don't actually know that it's on the unit circle, so I'm just going to call it r. how would you guys find R? If you knew the ordered pair. X squared plus y squared equals R squared. So you would probably use the Pythagorean theorem. I'll do it this one time, but from now on we'll just kind of all be like, okay, yeah, we know R is the square root of x squared plus y squared. But I would set it up, and of course I want to solve for R, so I'm going to square root both sides. R is the square root of x squared plus y squared. There is no property for splitting this up, this addition, so you can't do like x plus y or anything like that. That's what R is equal to. The square root of x squared plus y squared. Could it be equal to 1? Yeah, it could be a point on the unit circle, but it can also equal anything else. Like, we don't know what the radius is going to be. And then, if you're looking at the picture, you can generate all your trig ratios thinking about your old SOHCAHTOA from geometry. Sine is supposed to be the opposite y over hypotenuse, which is r. So this will be y over r. Cosine is adjacent over hypotenuse, x over r. Notice that sounds a lot like our rule for the unit circle. Sine was y, cosine was x. But because their r's were always 1, it simplified real nicely. Now we have to leave the r in there. And then, of course, tangent is y over x. And it's pretty easy to do the reciprocals. R over y, r over x, x over y. Now, one thing I should note, and I think it would be a good idea for you to mark something down about this in your notebooks, is that up here when you find r, the radius, r is always positive. You might remember that from Algebra 2. You can think about r as if it were like the radius of that circle, and so it's always got to be a positive value. It's never negative when you solve for it. Okay. But here's the weird thing. The sides of your triangle, your x and your y's, they can be negative, right? Depends on which quadrant they're in. If your triangle's in quadrant 2, x will be negative, y will be positive. If it's in quadrant 3, x and y will both be negative, and if it's in quadrant 4, x will be positive, but y will be negative. So your x and your y can change signs because it's talking about direction on the unit or on the coordinate plane, but your r will always be positive. Okay, so have a little conversation with your groups and see what you would do for this particular problem. You actually did problems like this last year. Let negative 2, 3 be a point on your terminal side of theta. Find the sine, cosine, and tangent. I would say to the groups, there's probably 2 ways I commonly see people start this problem. So kind of share out with your group, what are you guys going to do first? And maybe your group will work it out 2 different ways. So if you know negative 2, 3 is a point on your terminal side, find sine, cosine, and tangent. Okay. There are two different ways I think I see people normally start this problem. Okay. Here's one way I see. This is the smaller group of people in this room, but this is one way I see people working this out. So they say that -2 is x, and of course y then would be 3. And they know from the definition that we just copied down that r is the square root of x squared plus y squared. So I'm seeing people just jump in and do, what, 4 plus 9? So r equals the square root of 13. And then, if you remember the definition, like that box, that sine is y over r, cosine is x over r, and tangent is y over x, then you can do the trig ratios, right? So we would say the sine of theta is 3 over square root 13, which is 3 square root 13 over 13. The cosine of theta is x over r, so that's -2 over square root 13. Remember, r is always positive when you solve for it. And then the tangent, I mean, you could have done that one right away, is y over x. What, 3 over -2, so -3/2. That's one way to do it. That relies a lot on, like, you know the definition for sure. And you can, like, determine what the signs are. The other way, and this is probably the way I like to do it, it's really, like, I'm probably doing this, but at the same time, I'm just really quickly drawing out the triangle. So I like to do that just in case I forget about y over r, x over r, y over x. Remember that your angle theta will always happen right around the origin. Okay? And this was like where our terminal side passed through that point, but we created the right triangle. So I do this work to get my r value of square root 13, which will always be positive. And I can, of course, still do y over r, but I might be looking at more the way I've always done it in geometry, opposite over hypotenuse, adjacent over hypotenuse, opposite over adjacent. Okay. Either method is fine. The one thing you want to do is, like, whatever method you choose, make sure, like, when we're checking answers together on homework, that you're getting the correct signs, positive and negative. Because that's where people who do my strictly algebra and no picture thing usually have the most errors, is getting their trig ratios to be the correct signs, positive or negative. A nice thing if you're going to go strictly algebra and no picture is maybe just think about all students take calculus. So you can tell that this point is in quadrant 2, so sign should be positive and everything else should be negative, which is true in my ratios. And then just as a side note really quickly, some people get bothered by my -3/2 right here. They would say, well, isn't it supposed to be 3 over -2? Well, 3 over -2 is the same as -3 over 2, or like having a negative out front and a 3/2, right? So it's just saying that one of them, y or x, was negative and one of them was positive. Okay, now I'm going to switch it up. I'm going to do a different type of problem. Okay. Given that your cosine of theta is 2/3, cosine of theta is 2/3, so I might be thinking about my definition. Cosine is x over r, or I might be thinking about geometry. Cosine is a over h, right? Like, there's multiple ways for me to think about that. And the tangent of theta is greater than 0. That means that the tangent is positive, right? So this is saying that we have a positive tangent, and here we had a positive cosine. Can I find the cosecant of theta? Okay, and I'd just be thinking about, this is what I want my answer to be. Remember, the cosecant of theta is going to be r over y. So I'm going to need to find that y value. Since both cosine and tangent are positive, where is my triangle? Where's my point? In which quadrant? Hannah says the first quadrant. If cosine is positive, then secant is positive. If tangent is positive, then cotangent is positive. What's the only quadrant where more than one trig ratio is positive? Quadrant 1. Which leads us to believe that our answer cosecant is also going to be positive, right? So you can think ahead to your answer, like you know your answer should be a positive cosecant. If you're a visual person, then you can draw that triangle in quadrant 1. And whether you did A over H or X over R, you can label that. And you can find the missing side. Okay. Here I might go back to like regular old Pythagorean theorem, right? 9 equals 4 plus, let's say, y squared. So 5 equals y squared. Now on this one, when I take the square root, y will either be positive or negative, but not both. How will you decide what sign to give your y? Well, just look at where it is, right? So would that y value be positive or negative in quadrant 1? It would be positive. So now we know that y is positive square root 5, so I can answer the question cosecant theta is r over y rationalized 3 square root 5 over 5. Because I'm in quadrant 1, all trig ratios are positive, so I leave my cosecant to be a positive. These problems, I think, are kind of like more like puzzles. I'm giving you a few pieces of information, and then you've got to piece together like in which quadrant it is, whether you have X or Y, whether they're positive or negative based on your quadrants, and then do the trig ratio that it's asking for. So I'm going to give you time to do one on your own. Okay? And this is the place where I say be really careful, especially if you're going without a picture. Think about all students take calculus, because this is where I get a lot of people lose points for incorrect positive or negative answers. So given that the tangent of theta is negative 4/7 and the sine of theta is less than 0, can you get me the secant? I'll give you some time to work, and I'll put up my answer. Let me know if you're having trouble deciding a quadrant. I might be able to help you. Okay, I might start thinking about this one. Oh, tangent, that's nice. I basically got an x and a y, right? The one thing that you don't know about that because it's negative is like which one of those y or x is negatives. Because it could be -4 over +7, or it could be +4 over -7. How you'll know which one is positive and which one is negative is really like once you figure out which quadrant it's in, right? So that you'll know the movement of your x and your y. So we have a negative tangent right here. And then we also have a negative sign because it's less than. Well, tangent is negative in quadrants 2 or 4. Sine is negative of those in quadrant 4 because it's y. It's usually it's always positive in quadrant 2. So now we know we're in quadrant 4. So you could draw yourself a picture. Again, I rely pretty heavily on pictures. I think I get more right answers in terms of positives and negatives if I draw a picture. So I tend to like to do that, but you don't have to. But this now tells me for x and y, if I'm starting at 0, 0, x is positive. So this must be 7. Y is negative, so that must be a -4. And obviously my triangle isn't drawn to scale, but to me that's no big deal. When you solved for r, you got the square root of 65. And then secant is r over x. So the secant of theta is square root 65 over 7. I should find my answer. At the end, it comes together really nicely. Like, you've got all the things that you need, so it's not really hard to name that ratio. It's the beginning part where you really think about the quadrant and the location. If I was doing that all algebraically without the picture, I would have, it doesn't really matter which one of these I give positive or negative. I would still find the r to be square root 65. And I would know that secant was r over x, so I do square root 65 over 7. And then I would test all students take calculus. I would still say that I'm in quadrant 4 because of the signs of the trig ratios, so secant should be positive. Okay, last thing we want to talk about really quickly are reference angles. Now, I have, throughout our notes this chapter, I have probably said the word reference angle every day. And we've been using the idea of a reference angle to generate the angles on the unit circle and to do other things like the stuff we just did. We were relying on reference angles. But now we're going to just finally define them and talk about how to get them. So one thing to note about reference angles, your answer to a reference angle has to be two things. It's got to be positive, so negative answers no good for reference angles. And then it also has to be acute, so it's got to be between 0 and 90. This is the angle that's formed by the terminal side of your angle and the horizontal x-axis. So when you think about it, the reference angles are basically the angles on the bow ties. If you look at the back wall, okay, all of those triangles that I have set up, okay, where the triangle is in quadrant 2, that is its reference angle right there near the origin. It's positive and it's acute. I'm going to do some work for quadrants 2, 3, and 4. But before I do that, this bottom statement is really important. Before you ever get too far into finding a reference angle, I'll say this. It's easiest to find your reference angle, and you really should do this right away, is make sure that theta is between 0 and 360 or 0 and 2 pi. So if you have an angle that you're being asked to find a reference angle for, and it's outside of this range, it's beyond one revolution, one positive revolution of a circle, then I would do the coterminal angle first. Like I would get it in between those values. Because once you have it in between those values, then finding the reference angle is pretty easy for the different quadrants. In fact, if you get the angle to be between 0 and 360 and 0 and 2 pi, quadrant 1 is done, right? Like if your angle is in quadrant 1, it'll be between 0 and 90, so it will be positive and it will be acute. So if you get your angle in that range, you won't have to do any work for quadrant 1. Quadrant 2 will be a different story. So I'm going to draw out some work for quadrant 2. Here's what the quadrant 2 picture will look like. I got an angle in standard position. I've got it to be a positive angle between 0 and 360, so I've got my red arc showing that. And it lands in quadrant 2. This angle between the terminal side and the horizontal axis, the angle that it actually is, it's over 90 degrees, so it's not acute. The reference angle, which we call theta prime, is formed by that terminal side and the horizontal x-axis over here. So here's my theta prime. Note that in quadrant 2, if you get your angle between 0 and 360, then your angle and your reference angle add up to 180. So theta prime is 180 minus theta, or pi minus theta. You might remember that rule from last year. Always in quadrant 2. Okay, so if I have an angle like 140 degrees and I want its reference angle, I'm going to do 180 minus 140. There's 40 degrees left over. That's my positive acute reference angle. In quadrant 3, draw my angle in standard position. So I got my initial side on the positive x-axis, terminal side somewhere in quadrant 3. There's my arc showing that it's a positive angle within one revolution of the circle, right? You know, I have two ways I can go from the terminal side back to the horizontal axis, but in order for it to be the reference angle, I have to pick the one that's acute. So I'm going back to the negative x-axis always in quadrant 3. So here's my theta prime. You know, in quadrant 2, I think about the two angles make 180 degrees. In quadrant 3, I think about that reference angle is the overflow. I've gone beyond 180. So then I just have to switch my rule around. Theta prime is theta minus 180 or theta minus pi. So we actually practiced already doing the reference angles, like when we tried to do the tangent of 240. You know, like you might think about 240 as part of what bow tie. Another way to see that would be do 240 minus 180. That reference angle is 60 degrees. So you know that 240 has the same tangent as 60 degrees, just square root 3. And then you just have to decide, all students take calculus, it's positives. All right, and then you could draw a similar picture for quadrant 4. Put your angle, terminal side somewhere in quadrant 4. This time we're finally moving back over to that positive x-axis. So we're coming up right here is our theta prime. And then basically, like an easy way to remember this is in the fourth quadrant, if your angle is between 0 and 360, then that angle and your reference angle make 360. So you just have to subtract from 360. So theta prime is 360 minus theta, or, sorry, these are both theta primes, 2 pi minus theta. Now, those rules with the thetas don't work if theta isn't within one positive revolution. So you got to do that coterminal angle stuff first. So just really quickly, I'll show you an example so you're prepared for it when you see it on your homework. Okay. They'll ask you to do these two things with a reference angle. They'll ask you to sketch it, like sketch the original angle, and then they'll ask you to find the reference angle. So theta prime always means the reference angle. If I were sketching negative 600, I might first just find its coterminal. That will be an easy way for me to figure out where my terminal side goes. So I'm going to add 360, but that's still negative. Add 360 again, so that's like adding 720, so I'm at 120 degrees. So I can draw that angle. The only thing that would be different here is if I'm sketching negative 600, I have to show the direction and the revolutions. So I'm starting at the initial axis, I would go clockwise. 1 revolution, there's negative 360. And then I don't want to go another whole revolution because that would be negative 720. So I must just come up to that terminal side. Okay, so that's sketching the angle negative 600. And then they also want you to just tell us what theta prime is. Well, for theta prime, I would use this 120 degrees. It's in quadrant 2, so it's what's left over to get to 180. So 180 minus 120 is 60 degrees. Now, essentially, you've been using this reference angle idea over and over, okay? It's just like now it's embedded in our unit circle. So if we know the angles that are part of the families, like the bow tie families, we don't always have to figure the reference angle. Okay, you do have a homework assignment on the gold sheet. I won't technically be checking it until Thursday. So if you're a sophomore or a senior, you could plan to work on it like a study hall tomorrow. If you're a junior, maybe Tiny Times would be a good time for you to get that done over the next few days. Everybody should be studying and prepping on their unit circles, right? Let's plan for a unit circle quiz on Wednesday. We should know the unit circle very well by that time.